In this video, we're going to talk about how our solar system, the Milky Way, formed and the different types of planets that we find in our solar system. Our universe has millions, if not billions, of different galaxies inside of it. And each different galaxy forms through a nebula. Our galaxy, the Milky Way galaxy, formed about 4.5 billion years ago. Remember, that's the age of our planet as well. But all solar systems form in the same way, from the solar nebula, which is this absolutely gigantic cloud of material and dust and elements. But if this is a really hot cloud of just dusty material, gravity is going to develop. And it's going to start pulling material towards the center. But as it's pulling material towards the center, it's going to create a lot of collisions. And if you've ever been in a car wreck and touched your bent hood or fender afterwards, it's really hot from the collision. If we have billions of particles colliding near the center, it's going to start producing a lot of heat. It's going to heat up and ignite and create what's called the proto-sun. And this is just a prototype of our current sun. It was the very original one before it formed the one that we know today. But after this proto-sun formed, all of the material that's left in this gigantic cloud of dust, as it spins around this proto-sun, it's going to start flattening out into a disk, kind of like a vinyl album. But over time, as this disk continues spinning around, everything inside of that disk is going to cool down. And as it's cooling down and spinning, those particles are going to continue colliding. As they collide, they're going to join together and form larger and larger solid particles that are called planetesimals. And these planetesimals will collide together and eventually grow in size and form the planets that we know of today. But our planetesimals are just the very early original planets before they grew and ended in the locations that we know of. But our protoplanets, those prototype planets, are very different from our planets today due to something that's called chemical differentiation. As these protoplanets were forming, they weren't solid yet. Instead, they were mostly still liquids. And as liquids, that liquid's going to be able to flow throughout this protoplanet. And we're going to see that our really dense elements, those metals like iron and nickel, are going to start sinking towards the center of these protoplanets, while the lighter, more buoyant elements, our salty silicates, oxygen and hydrogen, are going to rise to the surface because they are lower density. And this is going to lead to all of our planets having different layers. You might recall that the Earth has a crust, mantle, and core, and they were all formed based on this chemical differentiation. Earth's core is full of iron and nickel because they're the densest, heaviest elements that sank when Earth was forming. And our crust is full of those silicates, the light elements that rose towards the surface as our protoplanet was cooling down and forming Earth. When we look at our solar system, the Milky Way, we'll see that the planets within it are all very different from one another. Some of our planets, like Venus, Earth, and Mars, have some atmospheric gases, where Venus and Earth have the thickest atmospheres. But we also see that farther away from our sun, we're going to get some planets that are extremely cold. They're so cold that instead of having solid rock like we have here on Earth, they just have really high amounts of ice. So we're capable of splitting our planets into two groups within our solar system. And we can split these into our solid terrestrial planets and our gaseous Jovian planets. Starting off with our terrestrial planets, these are the ones that are closest to the sun. And these 4 planets are Mercury, Venus, Earth, and Mars. All 4 of these planets are terrestrial, meaning that they're rocky, they're relatively small planets, and they're really dense inside. And while we have an atmosphere, that atmosphere has a really low escape velocity. An escape velocity is just how fast an object needs to go to escape our atmosphere. So when we're sending rockets into space, we need enough velocity for that rocket to exit our atmosphere. And here on Earth, it would just be easier to shoot off a rocket than it would in a place with a higher escape velocity. But the other 4 planets that make up our solar system are very different. These are called Jovian planets, and they're also occasionally called gaseous planets. And that's because these are formed out of gas. A lot of the times they're also called gas giants. These are gigantic planets, but they're also very low density because they do not have solid surfaces like Earth and Mars do. Instead, they have extremely thick atmospheres that are composed of gases like hydrogen, methane, and ammonia. And with these atmospheres, they're going to be able to freeze. So we're going to see that there are tons and tons of ice on these planets as well. But these planets have very high escape velocities. If we were trying to shoot a rocket off the surface of Saturn, we would need a whole lot more power and fuel than we would here on Earth. Our planets aren't the only objects that are orbiting around in our solar system, though. We have other things like asteroids that can eventually come and create a planetary impact. They can collide with the surface of our planet. And these collisions have happened throughout the entire history of our solar system. Since the Big Bang and our very first planets in our universe, this has been going on. But depending on whether the planet has an atmosphere or not, the impact's going to be either incredibly destructive or have little impact. So if we're looking at some kind of planet that has very little or no atmosphere at all, there's not going to be a lot of air resistance, meaning that friction will not slow that object down before it makes impact. So even the smallest pieces that are about to make an impact are going to have a huge destructive impact on the surface because it doesn't have anything slowing it down before it collides. But if we're looking at a planet like the Earth that has an atmosphere, our atmosphere is actually really good at slowing materials down as it's flying through before it ever hits the surface of the Earth. So if you've ever seen a shooting star, what you're actually watching is our atmosphere slowing down some kind of object, and most of the time it prevents it from ever hitting Earth's surface. But regardless of whether or not we have an atmosphere, if we have an object that's large enough, whenever it hits the surface, it can create impact craters. It's just going to be this large depression where something like an asteroid or a comet was actually able to hit the surface.